Welcome back to another Explainer. Today we are stepping right into the Class 12 Physics Lab, and I am absolutely thrilled to introduce you to our hero for today's session. It's the delicate, sensitive, yet incredibly powerful moving coil galvanometer. We're going to look at exactly how we can take this highly sensitive base instrument and upgrade it to handle some serious electrical heavy lifting. So here's a puzzle for you. How exactly do you measure a massive surging electrical current with an instrument that will literally burn out and break at just a tiny fraction of an amp? It's kind of like trying to weigh a bowling ball on a scale meant for feathers, right? But in physics, we don't just give up. We engineer a solution. We give our delicate tool a major upgrade. All right, here is our game plan for today. 1. Meet the galvanometer. 2. The half deflection method. 3. Finding figure of merit. 4. Converting to an ammeter. And 5. Converting to a voltmeter. Let's get to it. Section 1. Meet the galvanometer. Okay, so a galvanometer is a highly sensitive device used to detect very low, feeble electric currents. We're talking microamps here. It operates on a beautifully simple principle. When you put a current-carrying coil into a uniform magnetic field, it experiences a torque. This magnetic torque is what actually causes the angular deflection of the attached pointer. Basically, the more current, the more it deflects. This makes it brilliant at detecting tiny currents, but as you can probably guess, it's incredibly vulnerable to high ones. Section 2, the half deflection method. Now looking at our setup here for the half deflection method, key K1 controls the main circuit that's connected to a high resistance box, which we'll call R. Then we have key K2, which connects across our galvanometer with a smaller parallel resistance, and we call it a shunt, or S. So picture yourself at the lab bench right now. First thing, you pull a high resistance, let's say 2,000 ohms from box R, and insert key K1. We have to use a high resistance right off the bat so we don't accidentally burn out the coil. You adjust R to get a maximum even deflection on the scale. We'll call that angle theta. Next, you insert key K2. Without touching R at all, you just adjust the shunt resistance S until that pointer drops to exactly half of its original deflection, theta over 2. By doing this, boom, you've perfectly split the current equally between the galvanometer and the shunt. And because that current divides equally, we can take those lab values and calculate the base internal resistance. Galvanometer resistance G equals R times S divided by R minus S. You run this calculation a few times, take the mean, and you have successfully measured our hero's base internal resistance. Section 3. Finding figure of merit. The figure of merit, which is represented by the symbol K, is simply defined as the current required to produce a deflection of exactly one single division on the galvanometer scale. It is essentially the reciprocal of current sensitivity. If you know K and you know the total number of divisions N, you can very easily find the total current required for a full-scale deflection. Mathematically, it's pretty straightforward. To calculate K, you just take the total electromotive force, the EMF of your battery, E, and divide it by the total resistance of the circuit. That's your resistance box R plus the galvanometer resistance G multiplied by the deflection angle theta. In practice, you'll be taking a bunch of readings across different resistances and deflections, which allows us to calculate K for each one and find a really solid mean value. Precision is literally everything in experimental physics. Just notice how consistent those values in the final column are, hovering right around 2.19 times 10 to the negative 5 amperes per division. Section 4. Converting to an ammeter. So, to measure a large current, we obviously can't send it all through our sensitive coil. We have to equip it with some armor. We do this by connecting a very low resistance wire, the shunt, marked S, in parallel with the galvanometer, G. Honestly, the best way to think of the shunt is like a massive bypass lane on a highway, but for heavy electrical traffic. Because the shunt has such incredibly low resistance, almost all of that dangerous high amperage current takes the easy bypass route. Only a tiny, safe fraction of the current actually passes through the galvanometer coil itself. But since they are in parallel, the potential difference is exactly the same, which lets us accurately calibrate the dial to read the massive total current flowing through the main circuit. It's a brilliant workaround. Section 5. Converting to a voltmeter. Now, what if we want to measure the potential difference across 2 points? Well, we connect the voltmeter in parallel with the circuit component. But to stop the voltmeter from drawing too much current and actually messing up the circuit's voltage, we have to give our galvanometer a shield. Instead of armor, we connect a very high resistance in series with it. The exact value of this series resistance R is calculated using this specific formula. R equals the desired voltage range V0 divided by the full-scale current Ig minus the internal galvanometer resistance G. Let's put these upgrades side by side for a second. This is great to memorize for your exams. To make an ammeter, you use a low-resistant shunt connected in parallel to measure large currents. To make a voltmeter, you use a high resistance connected in series to measure potential difference. Having that stark contrast in your head makes the core principles so much easier to remember. So, there you have it. We've taken a highly sensitive, totally fragile piece of equipment and, just using a bit of clever circuitry, upgraded it to safely measure massive currents and high voltages. It really makes you wonder, right? By understanding a delicate instrument's fundamental limits, what other sensitive tools can we upgrade to measure the extreme forces of our universe? Definitely something to think about next time you step into the lab. Thanks for joining me on this explainer, and keep exploring.